A water main ground wire can be cut and re-spliced to make it longer. It is important to follow safe practices and ensure a secure, weatherproof connection. Firstly, turn off the water supply. Close the main water shut-off valve to prevent any water flow during the process. Secondly, locate the ground wire. This is typically a bare copper wire connected to the water main pipe using a ground clamp. It provides a path for electrical current in case of a fault, ensuring safety. Thirdly, wear safety gear. Put on gloves and eye protection to protect yourself from potential hazards during the cutting and splicing process. Fourthly, cut the ground wire. Use a wire cutter or hacksaw to cut the wire a few inches from the connection point. This provides enough space for making a proper splice. Fifthly, strip the ends of the wire. Remove about 1 inch of insulation from each end of the wire using a wire stripper. This exposes the bare copper conductor for making a secure connection. Sixthly, twist the wires together. Connect the bare copper ends of the ground wire by twisting them together tightly. Ensure a firm mechanical connection before soldering. Seventhly, solder the connection. Use a soldering iron and solder to create a strong and permanent electrical connection. This enhances conductivity and prevents corrosion. Eighthly, insulate the connection. Cover the soldered connection with electrical tape or heat shrink tubing to protect it from moisture and corrosion. Ensure a weatherproof seal. Ninthly, reattach the wire to the water main. Tighten the ground clamp securely to make a good electrical connection. Check for tightness to ensure proper grounding. Tenthly, turn on the water supply. Slowly open the main water shut-off valve to restore water flow. Check for any leaks around the spliced area. It's important to use a weatherproof connection method such as heat shrink tubing to ensure the splice is protected from moisture and corrosion. Moisture can degrade the connection over time, reducing its effectiveness. Also, make sure the connection is accessible for future inspection or maintenance. This allows for easy checks and repairs if necessary. Grounding is an essential safety measure in electrical systems. It provides a low resistance path for fault currents to return to the source, causing the circuit breaker to trip and de-energize the circuit. This protects people from electric shock and prevents damage to equipment. The National Electrical Code, or NEC, provides guidelines for grounding and bonding electrical systems. It specifies the size and type of grounding conductors, as well as the methods for connecting them to the grounding electrode system. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete encased electrode. The water pipe, when used as a grounding electrode, must be in direct contact with the earth for at least 10 feet. This ensures a good connection to the earth. The ground wire connecting the electrical system to the grounding electrode system is called the grounding electrode conductor. Its size is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. Bonding is another important aspect of electrical safety. It involves connecting all metal parts of the electrical system together to create a common ground potential. This prevents voltage differences between metal parts, which can cause electric shock. Bonding conductors are used to connect metal enclosures, equipment frames, and other metal parts of the electrical system. Their size is determined by the size of the circuit conductors. The NEC provides tables that specify the minimum size of bonding conductors based on the size of the circuit conductors. Ground fault circuit interrupters, or GFCIs, are another important safety device. They detect ground faults, which are unintentional electrical paths between a hot conductor and ground. When a GFCI detects a ground fault, it quickly trips the circuit, preventing electric shock. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of electric shock. Arc fault circuit interrupters, or RFCIs, are similar to GFCIs, but they detect arc faults, which are dangerous electrical arcs that can cause fires. SIs are required in certain locations, such as bedrooms and living rooms, where there is a higher risk of arc faults. Surge protective devices, or SPDs, protect electrical equipment from voltage surges, which are sudden increases in voltage that can damage sensitive electronics. SPD are typically installed at the service entrance to protect the entire electrical system. They divert the surge current to ground, preventing it from reaching the equipment. Proper grounding and bonding are essential for electrical safety. They protect people from electric shock, prevent damage to equipment, and reduce the risk of fire. It is important to follow the NEC guidelines and consult with a qualified electrician to ensure that the electrical system is properly grounded and bonded. When splicing a ground wire, it is important to use the correct materials and techniques. The splice should be mechanically strong, electrically conductive, and protected from corrosion. The NEC specifies the types of connectors and methods that are permitted for splicing ground wires. It is important to use listed connectors that are specifically designed for grounding applications. These connectors are tested and certified to meet the NEC requirements. When soldering a ground wire splice, it is important to use a soldering iron with sufficient heat capacity. The solder should be a lead-free type that is specifically designed for electrical applications. The soldered connection should be smooth and free of voids or cracks. After soldering, the connection should be cleaned and insulated to protect it from corrosion. Electrical tape or heat shrink tubing can be used for insulation. It is important to choose a tape or tubing that is rated for the voltage and temperature of the application. The insulation should be applied in multiple layers, overlapping each layer to ensure a complete seal. When reattaching the ground wire to the water main, it is important to clean the pipe surface thoroughly. Remove any rust, paint, or other coatings that could interfere with the electrical connection. A wire brush or emery cloth can be used for cleaning. The ground clamp should be tightened securely to make a good electrical connection. The NEC specifies the torque requirements for ground clamps. It is important to use a torque wrench to ensure that the clamp is tightened to a correct torque. Over-tightening the clamp can damage the pipe, while under-tightening can result in a poor electrical connection. After tightening the clamp, it should be inspected to ensure that it is properly seated on the pipe. The clamp should be free of cracks or other damage. The water main should also be inspected for any signs of corrosion or damage. If the water main is corroded or damaged, it should be repaired or replaced before reattaching the ground wire. The location is Plano, Texas. It is important to consider the local climate and soil conditions when grounding electrical systems. In areas with high moisture content or corrosive soils, it may be necessary to use special grounding techniques to prevent corrosion. The NEC provides guidelines for grounding in various environments. It is important to consult with a qualified electrician to determine the best grounding method for a particular location. Remember to always disconnect power before working on any electrical equipment. Use appropriate personal protective equipment and consult a qualified electrician for any complex electrical work. It's also worth mentioning that the size of the grounding electrode conductor is crucial for effective grounding. NEC Table 250.66 dictates the size of the grounding electrode conductor based on the size of the service entrance conductors. For example, if the service entrance conductors are 2/0 copper, then the grounding electrode conductor must be at least number 4 copper. Similarly, NEC Section 250.53 covers the requirements for grounding electrode systems and ensures that the grounding system provides an effective ground fault current path. This includes properly bonding the metal water pipe to the grounding system with a bonding dumper of appropriate size per NEC Table 250.102 cone. It's important to remember that a grounding system should have low impedance to provide a safe path for fault currents. High impedance can lead to elevated touch voltages during a fault, which could be dangerous. Regularly inspecting and maintaining the grounding system is crucial. Check for corrosion, loose connections, and damaged components. Periodic testing of the grounding system's resistance is also advisable to ensure it meets required standards. A ground resistance tester can be used to measure the grounding electrode system's resistance to earth. The NEC recommends a resistance to ground of 25 ohms or less. If the resistance is higher, additional grounding electrodes may be required. Also, Always adhere to local electrical codes and regulations, as they may have specific requirements for grounding in your area. Consulting with a licensed electrician is always a good idea, especially for complex electrical work or when dealing with older electrical systems that may not meet current standards. By understanding grounding principles and following safety guidelines, you can ensure a safe and effective electrical system in your home or business.